and you are trying to somehow fit your idea of reality, which is not based on observation, into the observable universe. For me, I'm always wondering, how can I have confidence about such a thing when my only confidence about reality in everyday life is the observation?
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. Quantum mechanics is a strange theory. Dr. Richard Feynman said, "I think it is safe to say nobody understands quantum mechanics." So why is this theory so popular if nobody even understands it? How is this the basis for all of our physical knowledge of particles and their interactions? Well, quantum mechanics, what I've learned going through physics as an undergrad and a graduate student, quantum mechanics did not come from a philosophical deep understanding of the structure of reality. It came from observations made in repeatable experiments on particles. And these observations could not be explained by classical means, by assuming that the particles had a reality when they weren't being observed. And that's horribly difficult to understand. For a long time, physicists were unable to decide if fundamental particles acted like billiard balls or like waves. And neutron scattering experiments showed that these objects acted like tiny billiard balls, or nuclear scattering, I should say. This duality between acting like billiard balls and waves was unlike anything anyone had seen in a macroscopic sense. There's no good analogies in everyday life to this behavior. The strangeness of quantum mechanics was best seen in the dual slit experiment, where you direct a stream of subatomic particles at a screen with two slits. And instead of getting two hills on a detector, on a piece of film behind those slits, what you see is an interference pattern of peaks and valleys, as though the particles were waves being pushed through that pair of slits. But when they hit the screen, they showed up as dots. They were, again, back to billiard balls, tiny billiard balls. And what does it mean? Physicists have found that if you can find out enough to distinguish between the paths that a particle takes, the interference pattern disappears. If you look at the particles as they're going through, if you tag them in some way, they no longer interfere. They become distinguishable. But if they're indistinguishable, you get interference. And this means that we don't know what's going on from analogy. What does it mean? About a century ago, we found that the Schrodinger equation of quantum mechanics accurately describes the progress of the wave function of any system of particles through any experiment. And it can be used to determine the probability distribution of large numbers of particles going through repeated interactions. But it said nothing about how an individual particle goes through. It said nothing about how particles turned from waves into particles, or when they were each different one. It was up to the physicists to interpret this, to get a consistent interpretation of the math. And this was coined as the measurement problem. What aspect of a measurement collapses this distributed wave function to a single point-like interaction? Nobody knew. There are no arbitrary constraints on this interaction. This is just something that physicists say, okay, we've observed it, now it's here, the wave function has collapsed. But what aspect of the measurement collapses the wave function? Do you need to be an intelligent observer to do this? Do you just need an atomic interaction, an energy sharing interaction? Nobody knew. What are the possible interpretations? Many physicists feel uncomfortable dealing with the philosophical implications of this problem. The only thing we do know is that the theory, as far as it goes, is unequivocally, unquestionably correct. It's the most highly verified physical theory that we have, and it's been measured to something like 23 orders of magnitude to be correct through very precise experiments. And there's been several different interpretations. The Copenhagen interpretation, 100 years ago, got us the basic idea that the wave function is just a probability distribution, and by calculating the magnitude of this wave function and integrating over your measurement space, then you get the probability that a particle will end up there. And that's all it says. But there are other interpretations that try to give reality to the particles. The many worlds theorem says that the wave function never collapses, and the particles have a basic reality, as far as I understand, and making a measurement doesn't collapse the wave function, but it tells you which of an infinite number of universes you're actually in. And until you make that measurement, you have this probability distribution of universes that you might exist in, and all these universes are overlapping and interfering. A recent innovative experiment fires neutrons through a double slit and proves that each neutron goes through both slits at the same time. If you like what you're hearing, please press like on your podcast app, share it with your friends, or join us to discuss these experiments on my Facebook group, The Rational View. Professor Holger Hofmann studied physics in his hometown of Stuttgart, Germany, then went to Tokyo University for a post-doctoral fellowship in 1999. Now at Hiroshima University, his research is focused on the way quantum theory describes observable phenomena. He believes that the key to a proper understanding of quantum mechanics can be found by exploring the practical means that we need to employ to achieve optimal control over a physical system. Dr. Hofmann, welcome to The Rational View.
Thank you.
Dr. Hartmut Lemmel studied physics in his hometown, Vienna, and graduated at the Vienna University of Technology in the group of Helmut Rausch, who is the father of Neutron Interferometry. After his PhD in 2007, he stayed in the group and was posted to the Institut Laue-Langevin in Grenoble as instrument responsible for the Neutron Interferometry setup. Dr. Lemmel, welcome to The Rational View.
Thank you.
So together, you have recently published what I consider to be a groundbreaking paper called Quantifying the Presence of a Neutron in the Paths of an Interferometer. And I just want to read the abstract, and then we can discuss. So the abstract says, it is commonly assumed that no accurate experimental information can be obtained on the path taken by a particle when quantum interference between the paths is observed. However, recent progress in the measurement and control of quantum systems may provide the missing information by circumventing the conventional uncertainty limits. Here we experimentally investigate the possibility that an individual neutron moving through a two-path interferometer may actually be physically distributed between the two paths. For this purpose, it is important to distinguish between the probability of finding the complete particle in one of the paths and the distribution of an individual particle over both paths. We accomplish this distinction by applying a magnetic field in only one of the paths and observing the exact value of its effect on the neutron's spin in the two output ports of the interferometer. The results show that individual particles experience a specific fraction of the magnetic field applied in one of the paths, indicating that a fraction or even a multiple of the particle was present in the path before the interference of the two paths was registered. The obtained path presence equals the weak value of the path projector and is not a statistical average, but applies to every individual neutron, verified by the recently introduced method of feedback compensation. Wow. Holger, could you provide some background on what motivated this particular experiment?
Okay, yeah, well, there's a lot of background here, and thanks for reading the whole abstract. It's quite a lot, right?
Yes.
Yeah, so it's been an old problem, really, what actually happens between sending in a particle into an interferometer and detecting it at the output. And the conventional wisdom is really that we cannot tell. So if we go back to the Copenhagen interpretation, it's basically just uncertainty. And if you measure the interference, you really know nothing about the path of the particle. But there has been some progress here, especially with the idea that you could make an interaction so weak that the interference doesn't disappear, and then maybe you could get a signal out. And on the average, actually, you would get the values that we also get. But there has been a big controversy because that's statistics and the noise is huge. And this new method that actually I introduced basically just 1 year before, this new method using a feedback basically confirms that this weak value is completely accurate and has no errors. Now, the reason why this is possible is that we focus on the amount of change that the system obtains. In this case, that's the rotation of the spin. And if you look at the details of the paper, the spin of the neutron is really the probe. It gets rotated. And the normal problem is that the spin is so quantum noisy, so uncertain, that if you just look at the spin, you don't see much information. But what I found is that the trick is really that if you compensate the rotation and then look in the direction where the spin is maximal, basically detect it at 100%, always in the same direction. To do that, you need the information how big the angle of rotation is. That's why it doesn't work in the forward direction. There's this old paradox that if you could measure where the particle is before the interference happened, then you would normally argue that even if the interference doesn't happen, the same result must come out. So suppose that afterwards you just decide to measure which path the particle is in. We know that if you directly detect the particle in the path, you find it or you don't find it. That's just two possibilities. So the big paradox is when you do interference, how come the particle can be distributed? A lot of people would call that a paradox and even dismiss the possibility. But what we find is that the rotation angle is really determined in this fractional way. It's just that you cannot use the small rotation to get the information.
So what you're doing is you have an interferometer which has two paths that the neutron could choose randomly, thinking about it in a classical way.
Yes.
And in one of these paths, there's a magnetic field that rotates the spin of the neutron a little bit. And so from when I learned physics, it said if there's any which way information on an interferometer, it would destroy the interference pattern. It would just choose one of the two paths, and you'd no longer have interference. So what's happening here is that you're somehow providing some which way information and not destroying the interference. Can you explain how that works?
Yeah, the information has to be really small. The trick here is we are not using the information on the spin rotation to determine the path. We are determining the interference outcome. And then we make a conclusion from the interference outcome what the path should be and reverse the rotation. Right? So the point is that we can accurately test whether we have estimated the right rotation angle, even so we cannot read out the rotation angle in the forward direction. So this is actually a very tricky business with the difference between extracting information and verifying a hypothesis. So it's a little bit tricky because, you would normally say, this is not a measurement. The spin is not measuring the path. You cannot see the path by looking at the spin. But you can confirm the presence in the path by testing the spin.
And the measurement implies that you don't get some neutrons with the full rotation, some without. What you get is a fraction of the rotation in all of the neutrons. And this means that the neutron has split itself between these paths effectively, just like the wave function does. So the wave function splits up, and then the question is, what's the interpretation? And you have some interpretations that there's a pilot wave guiding a real small particle through one or the other of the paths, or you have other ideas that you have multiple worlds, and the measurement tells you which world you're in, and in one world the particle took this path, in the other world the particle took the other path, and these worlds interfere, and so you're basically showing doing an experiment which I think actually tests these interpretations. Was that the idea behind this?
I wouldn't say that's the idea behind that, but it effectively is like that. For my side, I can say that my whole interest here comes from what I said in the introduction, actually. I really don't think that we can make a meaningful argument about interpretations without considering what we are talking about in terms of the evidence. So you need to actually have an effect. And in fact, when we wrote the paper and we had a long discussion about this problem, what is the presence of a particle? And the problem here is that we all imagine that we know what the presence of a particle is, but in reality, this knowledge comes from thinking we can see it, thinking we can touch it. So if the particle cannot be seen or touched, it's actually a pretty difficult question what we mean by the presence of the particle. So that's, I think, is the big problem, for example, with the guiding wave theory, that these particles do not actually have any other role except that you claim that when you detect it at the end, it's because it traveled along a path that nobody ever saw. So we are imagining that we could make ourselves really small and look, where's the particle? But there is no physics to that. You can't do that.
This seems to be like the overlap of physics and philosophy.
Yeah, but it's rather important because a physicist also has to know what they're doing. And the danger is that we are actually using language in the wrong way. This has been overlooked, I think, in the very beginning of quantum mechanics. There's actually an interesting piece of writing by Heisenberg, where Heisenberg basically explains that quantum mechanics constitutes an abuse of language, but that cannot be avoided because the classical language does not work.
There is no classical analog to this situation, that you can't get a good feeling for what the heck is going on.
Right. There is no macroscopic experience, right? Okay, maybe Hartmut wants to say something about that. It would also be interesting because, of course, Hartmut is closer to the actual experiment and deals with what is happening there. So.
Yeah, well, I'm the experimentalist of this work, and in my group we are doing neutron interferometry since for a few decades already. And in the Neutron Interferometer, the neutron beam is split into two paths, and then the neutrons recombine. But it is done not with like laser waves, but it's with neutrons, which are massive particles. And if you look at the velocity of the neutrons and take into account the size of the apparatus, etc., you conclude that every neutron takes a tenth of a microsecond to pass the apparatus. But the intensity is so low that only every microsecond there is one neutron in average. So you see there are never two neutrons simultaneously in the apparatus, and still an interference pattern builds up. So it is a clear sign that it is single particle interference. It is self-interference. Each particle somehow feels both waves, goes both ways. So our finding is actually, in my feeling, I was not surprised. This is what I also always imagined. And if we talk about the pilot wave or interpretations like that, in my opinion, if you say every neutron is accompanied by a pilot wave, then it's an integral part of this particle. So if if you say, okay, the neutron itself goes only one way, but the pilot waves goes both ways, I think you haven't won anything. It's a semantic question.
I'm very tempted here to ask, even though I should know, but I would like to point out and ask about the final detection of the neutron. I mean, the neutron is actually detected in the end in a nuclear reaction, as far as I understood that. Yeah, that's correct. So
Right.
here's the tricky part for the pilot wave theory, because basically the pilot wave theory drops the use of the wave completely at the moment of this detection. So there's a little bit of a strange idea that this kind of interaction, this nuclear reaction at the end, is completely different in nature from the quantum mechanics we used before. Of course, I guess that in the experiment, the control of this process is not very precise, right?
Well, there's a certain volume. It's a gas cell where the neutron can be absorbed by helium-3 nuclei, and they then send out particles which are actually then detected. And yeah, in principle, one can find out where this happened exactly and
up
and
to
when
a
it
certain
happened.
precision, which, as a theorist, I would say
Yes,
the
yes.
precision is not that high, because if I would calculate the interferences that are involved here, and there are interference there, I mean, I would need information that I never get in the experiment in this case. Right?
Well, I mean, in the Neutron Interferometer, we don't need a very high resolution because we have only 2 exit beams. But there exists, of course, also neutron detectors with spatial resolution and time resolution. And of course, it's a question of technology and statistics, what accuracy you get out of it.
Maybe you could walk us through a little bit more through the hardware you need to make this measurement. How is this experiment set up, Hartmut?
So the Neutron Interferometer consists of a perfect silicon crystal. So that's a crystal about the size, 20 centimeter long. And there are 3 lamellas standing up out of a common crystal base. And each lamella is a beam splitter. So this is based on Bragg diffraction. The neutron beam with the right angle and the right wavelength is diffracted by the lattice of the crystal. And if you do it right, then you have a 50-50 chance that the neutron is transmitted or reflected. And this is then again in the middle lamella, where the neutron beam is reflected again towards each other. And then in the last lamella, the 2 beam paths are superimposed. And then they leave the interferometer setup in different directions, and then half a meter away or whatever space you need, you put the neutron detector and detect the neutrons. And in between, inside the interferometer, you have space to place spin flippers or spin rotators, absorbers, whatever you like. And yeah, although it's every single neutron which is going these 2 paths, the paths are macroscopically separated in the order of centimeters. So
you have 2 different paths, centimeters apart, and in what's the wavelength of a neutron? What's a wave packet that represents the neutron?
That's 2 angstrom, so 2 times 10 to the minus 10 meter. That's really small. That's the about the distance of 2 atoms in a silicon crystal.
Right. So the intrinsic size.
Very small, and that's why the interferometer is very sensitive to vibrations. For example, if you move one of these crystal lamellas by 1 lattice constant, you would introduce already a phase shift of 2 pi. And so you have to control the relative position between these lamellas really, really good. That's why they are made monolithically they're cut out of a single crystal, and which they are still physically connected, so that they are also kept in position, always kept in position.
So this is one big silicon crystal that has various interaction zones in it?
Right.
Wow. And then you have to basically get rid of vibrations of angstrom level.
Exactly. This sits on an optical table which damps the vibrations. The temperature should be uniform. It should not change because then the lattice constant changes, etc.
How long did it take to set this up, to make these measurements?
This particular experiment, for example, I think we had beam time of 2 weeks, and approximately it was 10 days alignment and then a few days data taking.
Wow, that's impressive. That's actually very quick.
Yeah, it should be mentioned. It's much quicker than we are in optics, but the reason is that, Hartmut and the guys are very well set up, really. So the equipment is already present.
That's it. We didn't have to develop new components or so.
Exactly.
We could use what we had.
Interesting. So were you surprised at the results, or was this what you expected to see?
Yeah, I expected it, but I was surprised that the theory can make this statement that it really applies to every single neutron.
Right. I wasn't surprised because the theory made me quite confident that this would be the result. But I have to say, when I discovered the theory, I was a bit surprised myself that this is possible. Right? So the essential point is really that before I too had thought of these spin rotations as something that you cannot directly observe or measure. And I hadn't thought of the possibility of compensating the rotation and confirming that nothing happened. That was really a new idea. And that changed the whole situation a bit. Right.
Right. So you're applying a compensation after they've recombined?
Yes. After the interference. So the trick here is that actually the theory also says that there's a quantum interference effect involved that actually changes the angle of rotation depending on which balance of interference you have. It's a little bit complicated. So this is precisely where quantum mechanics is quite different from classical physics. When I did the theory, and that's something that has not been considered enough, if you interfere whole operations, you can sometimes get a new operation completely out of two operations that were completely different. Right? So it's not the same as interference of waves. Right? It's really an interference of operations. So the story, what happened, is actually quite flexible. Right? And this is what happens to the spin rotation. So if you look at the spin rotation in the one path, it's this alpha rotation, and in the other path, there is no rotation. So you think these are the two possibilities. But after the interference, you actually get new possibilities. Now, you shouldn't say that it's after the interference, actually, because before the interference, you simply have ambiguity. In the end, and after the interference, you could undo the interference, then you would go back to ambiguity. So this is where you have to go all the way to the final measurement. And that's the confusing thing. In the end, this is where this thing comes in for me with the nuclear reaction at the very end, right? That's where things are finally pinned down. Because before that, all the interactions were too weak to establish their own reality. And that's a little bit different. This is actually where quantum theory comes into its own, in my opinion, right? That in the end, because when you imagine forces in classical physics, a force pushes something and there's a change. And the change is a fact. And quantum mechanics, there is absolutely no description of a change where you can then identify the amount of change inside the object. Yeah. So this is the price we pay, in a sense, for quantization, for this wave function stuff. Yeah? So
you said something completely different can happen that you're not doing to the particle. Could you give an example of what could?
Well, it's the rotation angle in our case, right? So this is this confusion. I mean, we think we do to the particle either the alpha rotation or zero. And then after the interference, we look at the particle and we actually, by this compensation, confirm that it was a 2/3 alpha rotation. That then leads to the conclusion that the best way to understand it is that the particle was 2/3 present in the path. But this actually shows that, this also shows that there is a bit of a problem with the typical Feynman path interpretation, because the Feynman path interpretation gives you the feeling that it's either here or there, even though it's superposition. But the superposition itself creates this fractional presence. What is important, what is very confusing is, I mean, the initial wave function itself is not enough, right? If you have an initial wave function, it could still be completely random. It could be 0 or 1, or it could be actually something else. In order to pin down the values, you need the final detection as well. So you need the initial preparation, the final detection, and the combination of two coherences creates these fractional presences, which creates this problem that you always imagine that if you want to find it in the path, you have to detect it in the path. And then the result is 0 or 1. But
Right.
if you don't detect the path, but detect something else, and that was also a development that happened in the early 2000s, right? That is in the paper also you might find, we talk about Osawa, the Osawa uncertainties, and specifically the Osawa-Hall uncertainties. And that has something to do with a measurement theory introduced by Professor Osawa here in Japan, Nagoya. This measurement theory evaluates the error of a measurement when you are actually measuring something completely different, possibly. So the measurement is all general. You don't have to measure this physical property. And then you still attach a physical value to the physical property for this outcome. And Professor Osawa showed that mathematically you can calculate an error of that. And it turns out that this theory basically predicts that the weak values have the lowest error. That was then discovered by Hall in Australia. So there's a connection here with the weak values. And Professor Osawa is also using the initial state and the final measurement outcome in order to talk about a completely different physical property. So to understand that better, it's good to use the idea of statistical correlations. You have initial information, and then you measure something that is correlated with what you want to know. The initial information is the correlation. It says, for this state, the relation between this property and the other property I want to know is given. So after I see the other property, I can add the two pieces of information. And it looks very much as if that was the case. And in fact, it's very consistent, only that the values you get are not the eigenvalues in this case.
So it's let me go over this one more time, just so I make sure I understand. So you're firing the neutrons into two paths, or into a path, and then it splits into two paths. You're doing a small spin rotation in one of the paths. You're putting a magnetic field that. So when the neutrons come in, are they spin aligned? Are they all?
Yes, they are polarized. They are prepared in a certain initial direction.
So you give. One path has a slight rotation on the spin vector. They come back together and interfere, and they choose a path, and then they are detected. And then you have a second magnetic field that can correct for any spin misalignment of the particles. So you can't actually measure how much spin they've had if they're interfering, but if you rotate them back a fraction of the amount of spin rotation that was given to the one path, you correct all of them back to aligned.
Yeah.
Wow. So you're actually not measuring the rotation at all. You're just canceling what rotation was given. And it's odd to me that it's not 1/2. Why is it not 1/2? Is this something that comes out of the math?
Because we deliberately changed the balance between the paths. And that has something to do with
Okay.
correlations, as I said before. Now, you can get 1/2. There's a slight problem with this. And actually the slight problem is not so slight, because when you balance the interferometer, you have almost 100% of the output only in one direction. And that creates a bit of a problem, because you should be able to also see the other direction. But when the probability is close to 0, it's hard to deal with that. Yeah? So you actually don't want to have perfect interference. It's much easier if you change the balance between the paths. In our case, we had 90% in one direction, 10% in the other. So then we can, in principle, see both outputs, right? It's not a 0% problem. But it also means something else about the, it changes from 1/2 to another value, because the imbalance between the paths corresponds to a correlation between the interference and the path. So the correlation is then changed. The 1/2 means basically no correlation. So you measure the outcome, and all you get is a confirmation, because in the 1/2 case, you would initially know it's equal probability in both, and therefore equal average intensity in both. And it just confirmed that this is always the case, and the particle really splits 1/2. But in our case, whether I measure the 90% port or the 10% port really makes a difference, because there's a correlation between the outcome and the path. So in the 90% outcome port, in the constructive interference, we get 2/3. But in the destructive interference at 10%, we get 2. Looks as if there's a double neutron in the one path.
Oh,
That has,
okay. You're throwing a wrench into my thinking here.
well, yeah, it is not that simple, because these are the anomalous weak values that have confused a lot of people.
By the way, Holger, yeah, I mean, this ratio we have chosen, this is arbitrary. We can prepare it to have any ratio. We chose some nice values, so that's why it's 1/3 and 2/3. But actually, these values are too nice, because 2 people already asked me, well, it's probably related to the quark structure. You know, every neutron has 3 quarks in it, so 1 quark goes left, 2 goes right. I just want to clarify, this is not the case. The quarks are not separated. We don't care about the internal structure of the neutron. It's the whole neutron which goes to 1/3 here and 2/3 there, for example.
And it should really be said that the 1/2 case also exists, but it causes problems because of the 0 probability prediction for the destructive interference. If you are doing the experiment too well, you are in real trouble. That's not what we wanted to have.
Wow. Okay. So but this is cool. To me, the philosophy of the interpretation of quantum mechanics, how this experiment bears on that is really interesting, because I never thought anyone would be able to come up with an experiment that would test, say, the many worlds theorem or the pilotwave theorem. But we have these theorems that kind of posit a real particle. That people are very uncomfortable with having wave functions represent the root of reality, and they want to have real particles existing. But quantum mechanics tells us that there's no hidden variables, that particles, when they're not being observed, don't have paths. And so we've come up with these philosophical ideas to maybe explain how they could have paths, and maybe the many worlds theorem posits that the wave function never collapses, and that an observation is just telling you which universe you're in, and each particle does exist and has real paths in all of these different universes, and you just don't know which universe you're in until you measure it. And I think this makes that an untenable interpretation. But
well, it's certainly a critical commentary on this. As I said before, for me, for a long time, it was really essential that there needs to be something you can observe. And the weakness of the theories that you just listed here and described very nicely is always that these things are not observed, and you are trying to somehow fit your idea of reality, which is not based on observation, into the observable universe. For me, I'm always wondering, how can I have confidence about such a thing when my only confidence about reality in everyday life is the observation? And I think that's my criticism of the theory. So what I think we have done, and which is great, is we have actually demonstrated that you can be a bit more careful with the experimental investigation of questions like where the particle is. And it is possible to design, in this case, not really a measurement, but a verification method that tells you something about the physics of the presence of a particle, which is not quite the same as the reality of a presence of a particle. And that's maybe what causes the confusion, because the idea of reality is going a little bit beyond effects and observations. And that's, I think, there's a misunderstanding that people who think they are realists think they are not philosophical. But what you mean by reality is a very philosophical question.
It gets back to the original controversy over dualism, right? The particle is both a wave. It's both a wave and a particle, depending on what it's doing. And if you're not observing it, it doesn't have a reality. It's the dreams that stuff is made of.
So, yeah, you could say that.
How certain are these results? What are possible confounding factors? Are there anything that causes you to hesitate about this result?
Well, from my side, I'm pretty much aware of what some of the criticisms are, because I get them all the time. I have been getting them for years and years, and I take them seriously. So I'm not dismissing that. So what the criticism here is basically is in this idea that you know where the effect comes from. Right? So it is actually a bit of a problem that we also discussed at length, that we are now saying that this spin rotation definitely comes from the presence of the particle. But there is, of course, a school of thought that tries to give more reality than that to, let's say, the mathematical description. So there is an idea that the interpretation that this rotation originates from the presence of the particle or from the magnetic field that the particle saw has the flaw that the way we calculate this does not include a mathematical definition of what a force is, or mathematical definition what a magnetic field, what the quantity of the magnetic field really means, let's say that. So there is this problem of the mathematics. And that's a huge impact on, for example, many world interpretation, which basically says that. It says the mathematics is in some sense superior to arguments like ours, where we are saying that for cause and effect reasons, it should be the presence of the particle that makes the rotation 2/3, right? And it can be very difficult to argue with these positions because, in some sense, these are Platonist ideas of physics. And in Platonism, or in a trivial version of Platonism, the idea is always that we are just in this cave and see shadows on the wall. So the experimental result is a mere shadow of a higher reality. And so it's kind of then saying, well, the mathematics is so beautiful. Why are you dragging it down to this rather low level of actually taking this compensation so seriously? And that also has to do with then the question, have we understood? Because of this experiment, one could actually argue that we have a new idea what entanglement is. But then a lot of people would actually now say entanglement is a thing in itself, like energy or so, it's a resource. So we are happy to basically say there are no individual objects anyway, everything is entangled. And we are cutting that deliberately into pieces again. So, that is why the first argument and the first discussion has to be, is it possible in modern physics and modern quantum mechanics to agree that we have to put experimental evidence first? Basically, the argument is skepticism. You say, you have experimental evidence, of course, the click in the detector and so on, that is not controversial, but you shouldn't argue that it shows anything. The mathematics tells you what the experiment shows. And you see that a lot, for example, many world theory and also Bohmian mechanics. That's what I said about the Bohmian mechanics. The click in the detector is taken as proof for the whole existence of the particle before, but it's just this end click of the detector. And then the argument is that it's done for the beauty and completeness of the theory. And then people normally argue in the opposite direction, is we want to believe this theory and now we prove it somehow. And I'm just thinking we should only talk about experimental evidence and try to find a larger variety of possible experiments.
This is how we learn about what is the proper interpretation. I think this we need more experiments like this to inform a better understanding of the physics, because I mean, really, quantum mechanics is an unfinished theory. It doesn't describe the measurement problem. It doesn't, there's the Copenhagen interpretation that the wave function is a probability function, and shut up and calculate.
Yeah, I would actually say I saw your description of the Copenhagen interpretation. I would modify that a little bit, because I wouldn't say I grew up with that, but almost grew up with the teachings of Heisenberg, especially. And there's a lot of depth in the Copenhagen interpretation. The biggest problem is it's a kind of agnostic interpretation. You are right about the shut up and calculate. In German, I would call that the Denkverbot. It's not allowed to think. And as a student, I was very upset about the Denkverbot. I didn't like that about the Copenhagen interpretation. But otherwise, it's very deep, because it basically emphasizes that you cannot really know about things that cannot be observed. But the big problem is that Copenhagen also doesn't actually tell you how to judge what you can observe. That's where the problem is, right?
Yes. It doesn't tell you what an observer is, or what classifies an observation.
Yeah. And also what things you can actually observe and whether there are things you cannot observe. When I was studying, I remember one time where I was really a bit upset from the quantum mechanics lecture, because everything was about the Hamiltonian and energy. And I think, what does that mean? Can we only measure energy suddenly? I mean, that doesn't make sense, because actually energy measurement is rather difficult. You don't have any intuition of an energy measurement, really. But still, I mean, so I taught you have to diagnose the Hamiltonian, and nobody really explains why. So,
I think it gets back to conservation laws, right? I mean, you have these conservation laws, and these things you feel must have some reality to them because they're conserved.
Yeah. And thermodynamics, of course, is very important. So thermodynamics uses the energy, and thermodynamics uses little else. We did mostly solid-state physics. And solid-state physics, you start basically with a material that has a temperature, and then you perturb it a little bit, and then something happens. And that is most easy to describe using the eigenstates of energy. But that's the problem, that you cannot really easily generalize that. So when I learned about optics, this whole thing collapsed very quickly, because in optics, that's absolutely not the case. So laser light is a coherent superposition of different photon numbers. It's absolutely necessary to use that because you get macroscopic waves. So
Interesting.
yeah.
So what is your interpretation of quantum mechanics? What do you think? I mean, this is something that we all want is a better understanding of reality. And is there a reality to understand even? I don't know. I don't know what to think.
Well, I wouldn't call it an interpretation really, but I have a tendency to, basically what I'm looking for in quantum mechanics is an explanation of actual experience. The way we experience the world should be explained in a consistent manner. And one thing where I'm a bit different from a lot of colleagues, at least, is that I'm basically saying, for me, reality starts from our side, from what we experience, and then we have to try to find our way all the way down. And the only way to do that is to understand the relation of causality that allows us to build all the machinery, like in the Neutron Interferometer, right? So there's a causal connection here. We build these objects, we make our crystals, we put them in the right place, we make sure they don't shake and so on. And these are all causal chains. They're basically creating the causes that ultimately will create the detection of the neutron at the very end. It's a long chain, but in this chain, we rely on causality. We rely on laws of physics that are not about reality at all. They are just about relations. I mean, for example, we do say, Hartmut is setting up this crystal, and we talked about this is amazing that it's basically precise down to the atoms, right? But of course, that is not, you don't basically see the atom when you do that. So the interesting thing is that you can do that, even so you're handling this big block of material. You've just made sure it's very good, very pure material. And then I don't know exactly what methods you used to fix that. I was always thinking about this, Bohr had all of these old pictures with the slits that are screwed down. And I was sometimes saying to students, the thing is, when you screw down something that's elastic, so you're basically fixing things with a kind of spring. So it's obvious that even though you don't see it, everything is shaking. And it's interesting that we're not normally aware of that. We just ignore that, right? And then we have to use some tricks if the experiment gets so difficult that you have to be very precise. Right?
So you're basically positing that, we're not attacking any underlying reality here, that we're measuring relations between observables, and you can be agnostic, as it, what was that German word you called it? Don't think. Don't go beyond the math.
Well, the Denkverbot is a negative word. I mean, I wouldn't endorse the Denkverbot, quite the opposite. And also, I would say here, I would say for me, atoms are real enough. I had this, there was an interesting conversation with Ephraim Steinberg years back when he actually visited us in Japan. He did all the weak measurement experiments and Toronto University. So we had an interesting conversation about the question of realism, right? So he was listening to me and then saying, but you sound as if you wouldn't believe that there's a backside to the moon because you haven't seen it. And I said, no, that is a complete misunderstanding. Of course, I very much believe there's a backside of the moon because I know that I could see it if I went there. And that's quite enough. So I'm not the fanatic kind of anti-realist here, but I would want to know, how do I experience that? So yeah, atoms are very real because we have several ways of experiencing atoms up to the point of putting one atom in a trap and actually seeing it. I think we should take that more seriously, that objects become real by interacting. And most objects interact enough.
But still, you can build an interferometer using atoms. Even you can use large molecules and build an interferometer of them.
So it depends on the context whether you can see them. If they're in this special interferometer that Hartmann has built, suddenly they're not real.
Yes, exactly.
They are still real, but they can be simultaneously at two locations.
Interesting. Wow, this is great.
Yeah. But that depends on the interactions. And this is the thing, the microscopic objects interact massively. And that makes them very robust, right? I'm always telling the students, and actually I did a calculation when I was the first time in Japan, it was 95 actually. I wrote down a calculation quantizing the moon. Because as you know, Einstein raised this question, is the moon there when nobody's looking? Now, my answer to Einstein would be spontaneously, it's pretty hard not to look. With regard to the moon is hard not to see. But there's actually a calculation here, and it's a fun calculation. I mean, I hope I get the numbers roughly right. So the angular momentum of the moon around Earth is 10 to the 68 h-bar. And when one photon comes from the sun and is scattered to us from the moon, that changes the angular momentum of the moon by 10 to the 15 h-bar.
Wow.
One photon. And you never really know how many photons are scattered by the moon because it's statistics, and basically root n photons is noise. So basically the moon is experiencing quite a diffusion of the angular momentum all the time. That is the measurement back action here, really. So it's no wonder that the moon is easily localized. It's an open system. It's super noisy. So this decoherence argument is very easy to make. And I would be saying just that the moon is really the sum of all the effects that the moon has. Only the moon has lots of effects.
Right. It's very well tied to the universe through interactions. That's an interesting way to think of things.
It's basically screaming loudly, "Here I am."
So this is a groundbreaking paper. I'm sure you're going to get a lot of publicity from it. What are you guys thinking about working on next? What's next?
Well, I have thought of, we have done different experiments also with weak values, like the quantum Cheshire cat, different things, but they were measured always as a weak measurement, which applies only to the whole ensemble. So one could think about which experiment can be refined by the new method to get really answers about each individual particle. And then what I also find interesting, right now we have used the interaction between spin and magnetic field. What if we can do something with the neutron mass and gravity, for example? Would this be possible? To look how a neutron is distributed in the gravitational field, for example. But that's a much weaker interaction, so it will be difficult.
One thing I would maybe want to suggest sometime is also to look a little bit at phase shifts. That could be done in something like a Cheshire cat scenario too. But there's an interesting thing about the uncertainty of our method. So there is actually a natural error that immediately occurs when you look at phase sensitivity. And there's an interesting relation to the information about phase that you can get out of an interference experiment and the uncertainty of the path. So we have been operating in the regime where you get no real phase shift information, where the interference is super stable against small phase shifts. If you go away from that and go in a region where it's sensitive to phase shifts, then actually you do observe fluctuation. Then you start to observe statistics again. But these are the Osawa Hall uncertainties, which, the the Wien group has also studied a lot. I think Stefan Sponer here is really interested in that. And we might actually also explore that a little bit more. And of course, I should also say here in our group, I'm just getting a bit busy with 2 doctor students who are trying to work in the theory direction on the topic. And I think it's worthwhile to really try to find out every detail of quantum interactions. So the thing that we really don't understand enough is how quantum systems interact and communicate the information about their properties. Once it's clear that the reality of the object comes from the interaction, it requires a much more detailed and much more resolved look at how interactions really work. I think I do hope that the young guys do a little bit in that direction, because they should be getting in on it too.
Oh, very interesting.
Yeah.
Well, I think we're getting to the end of our time slot here, and I appreciate you both for coming on and chatting with us about this amazing experiment, and looking forward to more in the future to elicit some more information about quantum mechanics and reality. And for coming on the show, I'm going to send you guys both a t-shirt for the Rational View. So thank you. Arigato. Donkashen.
Thank you. Danke auch.
Thank you.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.